SwayamPrabha. Digital India. Educated India.
A logical and a systematic approach to solving organic chemistry problems for CSIR-NET. In module 22, we will be looking at structure determination of organic compounds by IR, UV visible, NMR, proton and carbon 13 NMR and mass spectroscopic techniques. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. In this session, let us look at what we are going to learn. We will be looking at how to interpret and determine structures of organic compounds using spectroscopic data. Mainly, we will be focusing on UV visible, mass, NMR and IR spectra will be used for the structural determination. Let us look at the first problem. So this question was asked in June 2011. So this is based on ultraviolet spectroscopy. So the absorption lambda max 279 nanometer with epsilon 15 in a UV spectrum of acetone is due to. There were 4 options given, 4 type of transitions are given. The first one is pi to pi star transition. The second one is sigma n to pi star transition. The third one is sigma to sigma star transition, and the last one is pi to sigma star transition. So we have to identify this 279 nanometer peak absorption maxima is due to which one of the following transition. So before solving this problem, we need to understand what are the different type of transitions and how much energy is required for each transition. So here a list of various transitions are given. The first one, let us go from the bottom one. This is the sigma bonding. The electrons, if they are kept at the sigma bonding, they can undergo couple of different types of transitions or excitation. The first one is sigma to pi star transition. The another one is sigma to sigma star transition. And if you look at the electrons which are kept in the pi bonding orbitals, they can undergo pi to pi star transition or pi to sigma star transition. So these are all the 2 transitions possible. And when we look at the electrons which are kept in the non-bonding orbitals, they can undergo n to pi star transition and the n to sigma star transition. These are all the various 5 different type of transitions that are possible. And let us look at the energy of each one of them to find out this 279 nanometer peak may be responsible for which type of transition. So here the various transitions are given. Well, the first one is pi to pi star transition. The lambda max for this particular transition ranges from 170 nanometers to 200 nanometers, and these transitions actually have a very high molar absorptivity. So the epsilon value for these kind of transitions vary from 10,000 to 15,000, and these are generally shown by groups which are having the pi bonds. Otherwise C to C double bond groups show this type of transition. The next one is aromatic pi to pi star transition. So this appears around 190 to 225 nanometer lambda max, and they have the molar absorptivity of 6,000 to 11,000, and these are mainly shown by aryl groups. And the next one is n to pi star transition, which ranges from 260 to 290 nanometer. Obviously this is the one which is actually falling in our range, which is the 279, and the molar absorptivity is also less than 50. So in the problem it is given as 15. So this is less than 50, and these are shown by carbonyl groups. So the given transition generally, is happening due to n to pi star transition. And the next one is sigma to sigma star transition. This is generally not seen in the UV region, and alkanes are the groups which show these type of transitions. Pi to pi sigma star transition is very rare, and generally not many groups show this type of transition. And the next one is n to sigma star transition. This varies from 150 to 250 nanometers, and these are also shown by very few functional groups, and the molar absorptivity for this kind of transition ranges from 200 to 400 and these are mainly shown by hydroxy group. So from the value which is given as lambda 279, lambda max 279, we can say that that particular transition is due to N to pi star transition, which is shown by carbonyl groups or C double bond O. Let us move on to the next problem. This was asked in June 2013. So in the UV-Vis spectrum of a diterpenoid exhibited lambda max at 275 nanometers. The compound among the choices given below are, here we are given 4 options, A, B, C and D. We have to find out which one actually is going to have the corresponding lambda max at 275. Before solving the problem, we have to look at the structures of the compounds which are given here. And if you very carefully look at all the compounds, all of them are having a double bond. That is, 2 double bonds are present in all the type of compounds. They also have a carboxylic acid unit which is given here. So these are very common for all the compounds, and based on the number of double bonds present and the functional groups that are present, we can calculate what is the lambda max for that particular compound. So if you look at the 4 different compounds, the first compound, the double bonds are in 2 different ring systems. So these are called as heteroannular systems. And then the second one, the 2 bonds are within the same ring, but they are isolated double bonds. There is no conjugation present because there is a CH2 carbon in between these 2 double bonds. So these are not conjugated double bonds. And in structure C, both the double bonds are present in the same ring, and in D, one of the double bond is present inside the ring and one double bond is present outside the ring, that is a exocyclic double bond is also present. So all the structures, if you look at, they all have 2 double bonds, and except the B, which is a isolated double bond. So from the lambda max value, what we can say is the isolated double bonds, their lambda max value, the base value is roughly around 215. So that means compound B may not be the option for our given problem. So we have to look at the other 3 cases, A, C and D. Before solving the problem, we do need to know the basic rules which govern the UV excitation values. So there is a rule called the Woodward-Fieser rule, and we will be mainly focusing for this particular problem because every substituent have a corresponding contributing value. So we will not be looking into the each functional group's contribution. We will be looking at only the groups that are present in this given system. So the first one is we have to consider the double bonds. So whether the double bonds are homoannular, heteroannular and conjugated or isolated. So these are all the things we have to look into. Based on that, we can decide what is the base value for that particular conjugated diene. The second one is we have to consider the H replacement on the double bond with respect to either rings or substituents. So these are all the 2 things we will be mainly using to identify what is the right structure given in this particular problem. So let us look at all the 4 cases. A, B, C, D are given here, and here in the structure 1, the double bonds are in 2 different rings. So here this is called as a heteroannular double bond. So when we have a heteroannular double bond, the base value for this kind of double bond is 215 nanometer, and there are 3 ring residues are there which are shown in the color pink. These 3 carbons are part of the ring system. So these are called the 3 ring residues. Each one of them will contribute 5. So we have 3 ring residues contributing to 3 into 5, 15 nanometers. And the alkyl substituent, there is an alkyl substituent shown in the green color here, that will also contribute to the base to the value of the UV max, lambda max. So that is 5 nanometers. And there is a exocyclic double bond that is also contributing to 5 units. So if we add all these things, it is going to be 245 nanometers. 240 nanometers, that is the lambda max for this particular system. but in the given problem, the lambda max is 279. So A may not be the right structure. And when we go to the structure B, as we have talked earlier also, this is a isolated diene. For the isolated diene, we only have pi to pi star transition, which appears at 170 nanometers. That means this is also not the right structure. We can rule out structure B. And the third one is having a double bonds in the same ring. That is what is called homoannular diene. So for the homoannular diene, the base value is 253 nanometers. And this structure also has 3 ring residues, which is equivalent to 15 units. And there is also another alkyl substituent, which is 5. So this comes close to 273 nanometers. And the given problem has 279. So this is the close enough value. So most probably this is the right option for the given structures. And let us also look at the last one, which is structure D. So in the structure D, one of the double bond is present in the ring and another one is an exocyclic double bond. So this is basically a heteroannular diene. So the base value is 215 and there are 3 ring residues and there are 2 alkyl substituents, and then there is also an exocyclic CC double bond. So based on that, if we add the value, this is coming to 245 nanometers. So of all the values, the third structure is actually having the close enough value to the observed lambda max. So this is the right answer or the structure for the given compound. Let us move on to the next problem. So this was asked in December 2011. So this is related to a mass spectrum. So in the mass spectrum of a dodecahedron, the molecular formula given is C20H20. The approximate ratio of the peaks of M is at 260 to 261 is. 4 options are given, which are 1:1, the second one is 5:1, the third one is 10:1, and the last one is 20:1. So these are all the ratios at which the peaks 260 and 261 will appear for this particular compound. Before solving this problem, we do need to know why 2 different types of peaks, that is M and M+1 peaks are shown, that we have to see. Based on that, we can actually solve this particular problem. So let us look at the structure of the compound. The structure is given here. There are 20 carbon atoms are there with the molecular atomic weight of carbon, which is 12. If we calculate, there are 240 it is coming to, and there are 20 hydrogens are also there. For hydrogen, the atomic weight is 1.0078. So by using these 2 things, we calculate 260.15 as the base peak for this particular compound. So the M by Z value 260 corresponds to its molecular weight. And how we get the 261? So to know about the 261, we do need to know about the carbon 13 that is present. So in other words, the natural abundant carbon contains 1.1% of carbon 13 isotope present in it. So in other words, for every 100 atoms of carbon, 98.9 are going to be carbon atoms having atomic weight 12, and there will be 1.1 atom that will be having the atomic weight of 13. So based on that, if the number of carbon atoms are going to be high, then the number of isotopes are also going to be high. Based on how much is the extra isotopes that are present, then the M+1 peak will be shown accordingly. So in this particular case, to calculate what is the ratio of M and M+1 peaks is corresponding to 98.9 is to 1.1 is, we have to multiply by that the number of carbon atoms that is present in that organic molecule. And one important thing for using this formula is the molecule should not have any heteroatom. So this molecular formula, what is given is C20H20. So there is no heteroatom present. So we can directly use this formula. And when we substitute the value of N as 20, we are going to get a value which is equivalent to 22% of the compound is going to have the 261 peak. So 100 is to 22% if we calculate, that is coming to be around 5:1 value. So that is the reason we can exactly say the molecular ratio between the M260 and M261 peaks are going to be 5:1 ratio. Let us move on to the next problem. So this is also based on again the mass spectra. This question was asked in June 2014. So the mass spectrum of a product A formed in the following reaction exhibits M, M+2 and M+4 peaks in the ratio of about 1:2:1. The reagent HX and the product A are, so 4 different options are given here. So this is option A, this is option B, this is option C, and this is option D. So the first one uses a hydrogen fluoride as the reagent. The second one uses hydrogen chloride, or HCl is used as the reagent. And for 3 and 4, it is basically the HBr that is used as the reagent. And the different types of products are given. We have to identify what is the reaction that is taking place and what is the product that will be formed. Here we have a hydroxy unit. The hydroxy unit reacts with the HX and the hydroxy unit is replaced by the X unit. So if it is fluorine, chlorine, bromine, or the 3 different halogens that are involved in these reactions when we use different types of reagents. So based on that, we have to identify what is the correct structure. If you look at A and B, we have 2 different heteroatoms or halogens are present. In the first one, it is fluorine and bromine. In the second one, it is chlorine and bromine. But in C and D, both the groups are going to be the halogens which are present is one and the same, that is bromine atom. And the only difference between C and D are they are basically positional isomers. In the first one, the bromine is present in the benzylic position, and in the second one, it is present at the homobenzylic position. So that is the only difference. And based on that, we are actually going to find it out what is going to be the ratio of M, M+2, M+4, whether it is 1:2:1 or any other different ratio. So before solving the problem, we do need to know one thing, which is the very basic fundamental thing, that is the isotope ratio of the halogens we need to know. So for fluorine, it is only F19, that is 100% present. And when we talk about chlorine, the chlorine has Cl35 and Cl37, 2 isotopes are there, and the ratio of the isotopes are basically 3:1. And for bromine, it is bromine 79 and bromine 81 are the 2 isotopes which is in the ratio of 1:1. So from this value, let us look at what products are possible and what products are not possible. And if we go with fluorine, which is having only 1 isotope, that means the 1:2:1 ratio is actually not possible in this particular case, because the molecule has only 1 bromine atom. So the 1 bromine atom is having actually the isotope ratio 1:1. So that 1:2:1 ratio is not possible. So we can rule out the fluorine as the reagent. And there are 2 other options are there. Now we have chlorine and bromine are the 2 other options that are given. And if you look at the chlorine, chlorine is having the ratio of 3:1. So that means if you have a mixture of products, so what are the different types of mixture of product that is possible? One product where bromine is in the 79 isotope, chlorine is in the 35 isotope, that is one type of product. And the second one is bromine with the 79 and the chlorine with the 37, that is 2 molecular weight, 2 atomic weight increased product, that isotope. And the other one is bromine with 81 and the chlorine with 35. So these 2 will have the same atomic mass value, which is M+2. And the last one is both the isotopes are having the higher, both the halogens are having the higher isotope, that is 81 and 37. So that will be the M+4 peak. So the first one will be the M ion, the second one will be M+2, the last one will be M+4. So when we do the calculation of all the 3, since the ratio of both the chlorine 35 and 37 is in the ratio of 3:1, we can rule out they can never lead to 1:2:1 type product. So chlorine is also ruled out. Now we are left with only two other options where bromine is the only substituent. And if we look at the bromine, in the bromine case, both bromines can be at the 79 isotope in one of the product. In the other case, one of the bromine is 79, the other bromine is 81. So in both the cases, they are going to be bromine 79 plus bromine 81 only. And moreover, the ratio of these two compounds is again 1:1. So we can say this product may be 1. And for bromine 79 and 81, we can have 1. And the bromine 81 and 79, we can have the other one too. So 1 plus 1, 2. The ratio is going to be 2. And the last one is both the bromines are having the higher isotope. That is again going to be 1. So if you look at the ratio, total ratio is going to be 1:2:1. So bromine is the right compound which can actually show this 1:2:1 ratio. Now the product may be either C or D. So both products are possible. We have to identify which is the right one. And this reaction, the replacement of hydroxide by the bromine atom, is basically a SN2 type reaction. So in other words, a benzylic alcohol will only give a benzylic bromide. It will not undergo any rearrangement to give the homobenzylic product. So that means product D is ruled out. So this is not the product, and the right option for this one is product C. So let us move on to the next problem. So among the following compound that gave a base peak M/Z72 in EI mass spectrum is, this question was asked in December 2017, and 4 options are given: A, B, C and D. All of them are having a carbonyl unit. So we have to do rather than simply looking at what is going to be the product, we have to look at how the fragmentation of this molecule will take place, and based on that fragmentation, we are going to identify which fragment will have the base peak of M/Z72. So for this one, we are going to look at a very important rearrangement that is possible in the case of mass spectrometry, which is called the McLafferty rearrangement. So this McLafferty rearrangement is basically a two-step process. Here, this involves a 1,5 hydrogen migration, that is the gamma hydrogen migration with respect to the carbonyl group. So if you look at here, 1, 2, 3, 4, 5. So this is the 1,5 migration. That means from the carbonyl carbon, if you start from this oxygen and this carbonyl oxygen and the hydrogen migration is responsible for this type of rearrangement, and this leads to bond cleavage, and that leads to some intermediate, and whose base peak is the one we are actually looking at. So let us look at how the fragmentation will take place. So these are all like a homolytic cleavage. In other words, all these transformations are single electron transformations. So there is a oxygen has a lone pair of electron. One of the electron will be shifted between oxygen and hydrogen. The carbon hydrogen bond is broken homolytically. So one electron from the CH bond moves between the oxygen and hydrogen, and during the same process, the rest of the bonds are also cleaving. So we get the alkene product as a byproduct, and we also have the McLafferty rearranged product. And this McLafferty rearranged product in this particular case is an enol, and the enol easily undergoes tautomerization to give the stable carbonyl compound. And this is the most stable or the strong base peak which is observed in this one. And if you look at the number of carbon atoms, there are 1, 2, 3, 4 carbon atoms are there. 4 carbon atoms into 12 is 48, and there is 1 oxygen, and oxygen is 16. So we can write 16, and we have 3, 3, 6 to 8. 8 hydrogens are there. So if we add these two, we come to the value of 72, which is the base peak that is shown by this particular compound. So the compound A is actually the right option for this one. Let us look at the other cases also to rule out there are not other products which can actually give this particular M/Z72 on McLafferty rearrangement. When we look at the option B, we have a acetone as the final product. So here only 3 carbon atoms are there. 3 carbon atom is 36, and oxygen is 16, and we have 3 plus 3 6 hydrogen atoms. So the total molecular weight comes to around 58. So this is not the 72 number which is given in the problem. So the second option can be ruled out, even though the option B can also undergo McLafferty rearrangement. And when we move on to the third one also results in the same acetone type radical anion that will be formed in this particular radical cation that will be formed in this particular case. So here also we are not going to get the M by Z 72 molecular ion peak. And if we look at the last one cannot undergo McLafferty rearrangement. So based on that, we can rule out B, C, and D, and the final product is going to be, the right option for this one is going to be option A. Let us move on to the next problem. So here from now onwards, we are going to look at NMR spectra. The first one in this NMR problem is in this NMR spectrum recorded at 293 Kelvin, an organic compound having a molecular formula C3H3NO exhibited signals at delta 7.8 for 1 proton as a singlet, 2.8 for 3 hydrogen atoms as a singlet, and at 2.6 3 hydrogen atoms as singlet. The compound is 4 different types of compounds are given. This is asked in December 2012. And now, before solving this problem, we do need to have some basic idea about which NMR hydrogens peak will come, which are attached to heteroatoms. Say, for example, we have a N-methyl group, we have O-methyl group, and we also have a methyl group attached to the carbonyl group. So these are all the 3 different things. And if you look at in this problem, we have a O-methoxy group, that means attached to oxygen. Another one is attached to the carbonyl one. Here we have a O-methoxy. Here we have N-methyl. So these are all the different types of methyl groups that can come as a single peak, that is a singlet. So which in the proton NMR spectrum, where at what ppm they will come, we do need to know. The acetyl methyl generally comes at 2 to 2.2 ppm generally. And O-methoxy carbons, this methyl group generally comes at the 3.9 to around 4 ppm values it will come. And for the N-methyl, that will come around somewhere between close enough to 3 ppm or so, depending on where they are actually present. So they may come. So based on that, we can actually say whether N-methyl may be present or O-methyl is present or acetyl group is present. We can easily figure it out. In this one, we have 2.8 and 3.6 are the 2 methyl peaks which are given here. In that case, we can actually rule out the option C may not be present because it comes at around 2 to 2.2. And O-methoxy peak also may be ruled out because they generally come close to 4 ppm or so. So in other words, what we can say is option A, B, C, D, 4 are given, out of which B, C, and D can be ruled out. How we can rule out is basically based on which region they will come. And this is actually given in this particular case. So the N-methyl generally comes around close to 3 ppm, that is 2.5 to 2.9 ppm. O-methyl comes close to 4 ppm, that is 3.5 to 4 ppm. And acetyl comes around 2 to 2.2 ppm. So we can easily rule out many of the options, that is D can be ruled out, C can be ruled out, B also can be ruled out because none of these methyl groups appear as 2.8 ppm or 2.6 ppm. So that left with only one option where we have the N dimethyl group that is possible. But if you look at the N dimethyl group, these 2 methyl groups are chemically equivalent. So when they are chemically equivalent, we cannot have 2 methyl peaks. So what is the driving force or what is responsible for 2 different methyl groups that are shown in this compound? So for that, we have to go one step above, in which case there is a resonance that is happening in the case of N dimethyl formamide. So the lone pair of electrons on the nitrogen is in conjugation with the carbonyl group oxygen, oxygen being more electronegative than nitrogen, it pulls the electron towards itself. So we end up with a double bond between carbon and nitrogen. So because of the presence of a carbon-nitrogen double bond, now the free rotation of these two methyl groups are actually now frozen. In other words, there is a barrier to this particular rotation. In other words, one of the methyl will be present closer to the oxygen, the other methyl is far away from the oxygen. So based on that, now we can say these two methyl group will be chemically non-equivalent, and they show or they appear as two different singlet peaks, and that is what we are actually seeing in the NMR. So here, if you look at one of the methyl which is cis to the oxygen appears at 2.8, and the other one which is trans to the oxygen appears at 2.6. So that clearly tells the given compound is going to be NN-dimethyl formamide with the NMR values. So here the most important thing is the carbon-nitrogen double bond, which is responsible for the non-equivalence of both the methyl groups. Let us move on to the next problem. So here the organic compound that displays the following data in 1H NMR, that is at 400 megahertz. The delta values are given. The first one is 7.38 doublet, the second one is 7.25 again doublet, and the last one is 1.29 singlet ppm, and four options are given A, B, C, D. We have to identify what is the correct structure for the given NMR values, and this question was asked in December 2017. So if you look at all the four options which are given, we can try to figure it out what could be the right structures without getting in detail about each peaks. So we have a doublet 7.38 and 7.25. So this clearly tells that compound is basically a para-disubstituted compound. So this is a simple clue we can identify. So based on that, what we can rule out is D is not the right structure because it is a meta-disubstituted product. So here the para-disubstitution, that is a doublet and a doublet, two types of peaks are not possible for the meta-substituted product. So D can be ruled out. Now we have only A, B, C, three products are possible. Out of that, one is going to be the right option for this problem. So how do we know which one? Can we still eliminate other options? So if you look at B, the B has actually four different types of hydrogens. So one is the methyl hydrogen here, and here these two methyls are another set of methyl, and we have these two aromatic ring compounds. So that means we will be getting actually 1, 2, 3, 4. Four different types of peak should be there, but we are given only three type of peak. So B also can be easily ruled out based on simply without working out the problem. We are just trying to rule out what are all the options which are not going to be the structures. And if you look at C, here again we have three methyls which are equivalent. We have two types aromatic protons, and we also have a benzylic one. So here again, if you look at, there are 1, 2, 3, 4 types of signals are possible. So we can also easily rule out C is also not the right option. So we are left with only one option, A. So without solving the problem, we are just trying to rule out the options. So we are left with option A only. And if you look at A, we have all the tertiary butyl methyl group will come as a singlet, that is fine. And we have the para-disubstituted two hydrogen atoms. So we have only total 1, 2, 3. Three types of protons are present in this compound. So that means that exactly matches with the given one. So without exactly solving the problem, we actually know what is going to be the right option, that is option A. Let us work out this and find it out, like whether what we have talked is the right one or not. So let us look at the different types of signal. As we see, compound, the option A has three signals, that is X, Y, Z are the three types of hydrogens which are present, which are chemically non-equivalent. So we have three types of hydrogens, and when we go to option B, we have four different types of hydrogens, and for compound C also we have four different types of hydrogens, and for compound D we actually have 5 different types of hydrogen. So from that, it's very simple. We can rule out say B, C, D, like what we have seen earlier also, and the right option is going to be only A, and A is the answer for this particular problem. Let us move on to the next problem. So the number of chemical shift non-equivalent protons expected in the proton NMR spectrum of alpha pinene is. The structure of alpha pinene is given here. We have to find out how many are there. Basically, it is 6, 7, 8, 9 or 10. That's what we are going to see. And this question was asked in December 2015. So here, the structure of alpha pinene, if you look at, without drawing the bicyclic system in the chart type conformation, we will be quite confused to find out what is the exact number of non-equivalent hydrogen atoms. So if you simply look at the alpha pinene's normal structure, so we have a methyl group, we have a hydrogen here, and we have 2 gem dimethyl groups are there, so 1 and 2, and we have a hydrogen here. This is again 1 hydrogen is here, here we have hydrogen, here we have 1 hydrogen. So this center is a quaternary center, so there is no hydrogen. So these 2, the gem dimethyl groups are obviously going to be a single type. That's what when we look at this first structure we will see. So based on that, we will simply calculate all the methyl will appear as a singlet. So that means what are the different number of possible hydrogen atoms are this. Let us start from here. 1, this will be 2, 3, 4, 5 and 6. Then these 2 gem dimethyl we will have 7. So that means here again there are 2 hydrogen atoms are possible. Here again 2 hydrogen atoms are possible. So we may assume that these 2 hydrogens are going to be chemically equivalent. So we can simply say there will be roughly 7 different types of hydrogen atoms will be present. But if we draw that in the cyclohexane chair like bicyclic ring system, then we can actually look into little bit more detail about how each hydrogen are actually appearing in the 3-dimensional space. So here if we look at this particular structure, we have a double bond. That double bond is having a methyl group, and this is a rigid ring junction. So in that case, one of the methyl actually lies closer to the double bond, and the other methyl is little far away from the double bond. In other words, we can say this is like a endocyclic one, and this is a exo methyl group. So we have both the methyl groups are appearing at 2 different chemical magnetically non-equivalent environment. So they are going to appear as 2 different sets of peaks. So this is the crucial thing we have to remember while solving this particular problem. So if we look at the different types of hydrogen atoms in this particular molecule, then we have this methyl is different, and another thing, this alkenic methyl is also different. So we have 2, this hydrogen is different, and both the hydrogens are going to be different. Five, 6, 7, 8. So there are total 10 different hydrogens are actually present. So we started from this endo methyl group from the ring junction. So 1, there is another methyl here, 2, 3, 4, 5, 6, 7, 8, 9, and finally this methyl group which is in the gem dimethyl position. So all the hydrogens are going to appear at different places. So we have 10 different, that is non-equivalent protons are present in the 1H NMR spectrum of alpha pinene. So that way we can solve that answer as 10 different groups. Let us move on to the next problem. So here the structure of the compound that matches the 1H NMR data given below is, the NMR values are given. These are recorded at DMSO D6, and the first value is 7.75 doublet of doublet with the 2 coupling constants are given, 8.8 and 2.4 Hertz for 1 hydrogen atom. The second one appears at 7.58 ppm. It's a doublet with a coupling constant of 2.4, and this is mainly for 1 hydrogen atom. and we have another peak at 6.70, which is a doublet with J coupling constant of 8.8 Hertz for one hydrogen atom, and at 6.50 we have a broad peak which is for a 2 hydrogen atom, and we have a singlet at 3.8 for 3 hydrogen atoms. So these are all the different values which are given, and based on that we are going to find out what is going to be the structure of the compound which matches with the given NMR spectrum. This question was asked in December 2015. So let us work out how or which options we can actually rule out. Based on that, can we figure it out what is the right compound? So let us move on to the solving the problem. So here we have 4 different compounds. The NMR values are given here, and our first argument is going to be there is a peak, a singlet at 3.8, which is a OMe peak. So in other words, what we can say is the compound without a OMe structure can be easily ruled out. So we can easily rule out D, because here we have a acetyl is present here. This is basically the acetyl methyl is there, and this acetyl methyl appears somewhere around 2.2 ppm. So that can be easily ruled out.